as it is very clear from the name that we will try to predict the house prices of house in Boston. For that, we will try to find at one feature which is highly correlated with the price which we are taking. And first, we'll start from putting all the required libraries. Now, PyPandas, background is a Python for graph, for animation, and base variable function for showing the error from the created set and create test set, and create test set function for data. And okay, so what are the steps involved in solving a problem machine type? First step is data precursor, data, then I have function. Then we will try to split data into test data and train data. And then we will train the model using the trained data. And finally, we will predict the prices of houses on the test. Okay. So first data. So for that, we will load the data in the variable Boston, and we will describe the data, and then we'll describe that you will came to know that there are features. There are 13 features on which the price of house in Boston are dependent. Okay, and then we will create a data frame to show all these features in a table, column by column. And for that, we will create a data frame. And after that, we will create a data frame for showing the prices with the column name target. And then we will concatenate both these data frames in a single data frame so that we can compare those features with the target. So that is how we have created a single data frame of the features and the target price, which is the price of houses. And now we will use describe to generate observable data set. What describe is doing is that it is providing us all the statistics of the features. That is count of all the features. The 506, actually there are 506 columns, so the count. In the mean, we know CRIM 3.6, and we have target 22.5, age 3.5. These are all the statistics of the stats of all the features in the game. Now we are trying to know the correlation between the data, features, and the target price. And for that, we will use the correlation function here. So here we have find the correlation between all the features with itself, with other features, with target. But we only want to know the correlation between target and all the features. So what we're doing here is that we will define a variable post URLs, and we will put all the attributes, all the features for comparing with the target. So these are all the values which are written here, because you only want to know the correlation of the feature with only the column target. And now we will zip. Zip means we will that correlation and that list of features, we will zip that. And now we will know the correlation of features, corresponding features of that. Now we will try to sort this list according to the correlation value in the descent, so that we came to know about the highly correlated feature. Now we will unzip the data so that we can have two separate lists. Of one is for feature and one is for correlation values. And now we will plot the graph of the correlation values versus all the features. And these are the graph. So from here we can see that LSTAT is the highly correlated feature with the target price, with a value of greater than 0.7, and there's the RN with a value of slightly less than 0.7, and the ET ratio with a value of around 0.5. So as of now, we are only using linear regression method, so we will use only one feature to predict the price of the houses. So we will take LSTAT as a required feature. So we will get a data frame of LSTAT and we will put it into X, and we will get a data frame of target and we will put that into Y. As all the values of the X and Y are in their own range, which can't be compared with one another. So we will try to range those in 0 to 1 so that we can easily compare that. So for that we will use miniscalar function, and then we will reshape those in -1 to 1 and -1 to 1. So all the values are in between -1 to 1 so that we can compare them easily. And now we will split data into sets. So there will be a train data and test data. And this is a function which is used to split data into two data, train data and test data. Now third step is define error function. So we will define error function which will actually give the error or the difference between the trained data and the predicted value. So we have to minimize that. So what is the error function? Error function is this, and we will then define update function. These all functions will be used in gradient descent function. What gradient descent function is doing here is that it is taking the M and C value which we have initialized here. We can initialize this value with, we can initialize any of this, which we can initialize M and C with any values. So we initialize 0.7, 0.2, and we will give learning at 0.001, iteration 250, and iteration 0.01. And we have passed these all values gradient descent function. And what gradient descent function is doing is, it is providing M initial M and C equals to initial C. And then we are calling the, and we are defining the error values as a list and MC value is a list, and we are then for loop. We are writing a for loop in range iterations up to 250 times, and we are calculating error. If error is less than error threshold, then it's the for loop will break and print this statement. And if error is not less than error threshold, then that error will go into error values so that we can product the after that. And again, if we have to update MC values again and again so that the error will be minimized. So for that, M and C equal to update, we will call update function and pass XM, CT and learning it. So here these 5 values are there, and for that we have to calculate gradient M by this formula, gradient C by this formula, and after that we will calculate new M and new C by M minus gradient M into learning it, and M is equal to C by gradient. We will return that M and C. So here we will got new M and C, and we will put that MC values on a pair MC. So MC values is a list containing all the MC values. So again the function will call, and again the error function will be called, and the update function will be called, and it will iterate until the 250 iterations are completed, or if the error is less than error. So that's what the waiting conditions. So yes. So after all this gradient descent function, we will get to know that their MC values will come like this. This is the new MC values. Okay, and now we will visualize of the learning process. So what we'll do is we will plot the regression line against the training data. So we will we can know that how that MC values is working against the training data. So these blue dots, these are the blue dots which is plotted against the data which is already providing, and this red line is the predicted value against the X-trained data. So yes, and we have plotted error values against iterations. We can see that when the iterations are increasing, the error value is decreasing, and after certain points of iterations, the error value has become parallel to the iteration. So there is no change in the error value. So if we have taken greater than 250 or 300 value of iteration, then there will be no need of that, because the error values have already parallel to the success. Finally, our motive is to predict the price of house in Boston, and we will do that. For that, we will as in Python we can use, in NumPy we can use a vectorized operation. So directly we predict it equal to m into x test. This is a test data, x test, and these are m and c values are the values which we have got from this function m and c by calling here gradient descent function. We have got m and c values here. You can see that we have print m and these are the new m and c values which we will use to predict the prices of house in the cost of the test data. So yes, now we will calculate the mean square error. The error which it will tell us the difference between the actual value and the predicted value. So it is showing that 0.019 is the error between the y test and predicted data. And yes, we will get a data frame of x test, y test predicted, so we can see them in a single table and compare those. And this is the data. And now we will plot the predicted values and the target values. These are the predicted values. These are this is the two dots are the value which is already data, and this red line is the line which is the predicted value against the test data. Okay, and now as this data is not in the format that we can tell the price of the house, so we have to convert this data into data so that we can know the price of house in terms of $1,000, in multiple $1,000. So for that, first we will reshape that data, predicted data, x test data, and y test data into -1 to 1. First normalize the data, and then we will scale that or inverse transform. We have transform data in a range of 0 to 1. Now we will inverse transform data into actual values of those, so that we can know the actual price of data in terms of multiples of $1,000. So we will inverse transform that, and after that we will remove the extra dimension, or we will do slicing, because that data will be in a column format or vertical format. We have to change it to horizontal format, and for that we will do slicing. And these are the new scale data, extra scaled, by test scaled, and predicted scaled. So now the values will be in the multiple of $1,000 because of inverse transform. And now we will get a data frame, and we will zip all the x test scale, y test scale, and predicted scale in a single table. The columns in x, target y, predicted y, and we will round those to decimal to places, and we will show that table here. So these are the values. We will see that the target y is 24.7, predicted by 20.45. There's a minimal difference between that because the error is 0.019, so there should be a difference between the predicted value and the target value. So there's a difference. Okay, we will now finish this video here, and we have finally predicted the value of prices of house in Boston using the linear regression method. Thank you very much.